We're going to start a new topic on the perceptron algorithm. The perceptron algorithm connects to the previous discussion because it's a mistake-driven algorithm, and it's a mistake-bound algorithm, and it works and it learns a linear classifier. So we'll be looking at the algorithm itself and try to understand what it's doing. Then we'll look at some variants of the perceptron algorithm, and then we'll have a discussion about the perceptron mistake bound. In your next homework, you'll be implementing the perceptron algorithm and you'll be proving something around it. So let's start off with the perceptron algorithm. How many people have seen perceptron? Many of you. Well, not many, some subset of you. If you haven't, okay, we can go through it in some detail. The perceptron algorithm tries to learn a linear threshold unit. We've seen linear threshold units before, but just to remind you, we have a d-dimensional instance space. Namely, in other words, our instances are vectors with d elements, or if you want to be more boring than that, our instances are d numbers. It's an array of d numbers. And together, we'll call them x. And our labels, we are working with binary classification. And for usually, when we talk about linear classifiers or any of these sort of models that operate in vector spaces, we treat false as -1 and true as 1. So we have a binary classification problem where the label can either be -1 or 1. A linear threshold unit is defined by parameters w, a weight vector with d elements, and a bias term b, which is just a single number. And it makes prediction using a very simple rule. For any example x, which has d elements in it, every feature xi is multiplied with its associated weight wi to get a number. And you add up all these numbers, so you get sum of wi xi. In other words, that's equivalent to saying you take the dot product of w and x. And I write that as w transpose x. You get a number, w transpose x, and then you add the number b to that. You still have a number, and you look at the sign of it. If it's greater than or equal to 0, if it's positive or 0, then you say the label is +1. If it is negative, you say the label -1. This is the device that we are going to, that the perceptron algorithm learns. And by learn, I mean it will figure out, given a data set, values for w and b. Sometimes you see these sorts of cartoon examples for how a linear classifier might look like. Each feature is this node here in a graph, and the wires contain this x1 travels along this wire to this summation, and as it travels along that, it gets multiplied with the w1, and each of these gets, and the number 1, when it travels along the wire, it gets multiplied with the b. All of them get added up to get w transpose x plus b, and then you take the sign of that. This sort of a picture no longer is not seen a lot these days, but in early neural network literature, this was a very common thing. We've also seen that a perceptron is a linear classifier. In other words, it sorry, not a perceptron. We've also seen that the linear classifier has an interesting geometric perspective, where the separating boundary between the plus and the minus is a line in 2 dimensions or a hyperplane in high dimensions. The idea being there is a high dimensional space and there's a flat surface that cuts through the space and says one side is plus, the other side is minus. And the weight vector w is simply the normal to the to that hyperplane. It's the normal direction to the hyperplane. We've seen all this before. So now let's talk about the perceptron algorithm. The perceptron algorithm was invented by Frank Rosenblatt in 1957 or 58. I mean, the early versions showed up in 58. It was formally published in 1950. Early versions showed up in 57, and it was formally published in 58 in Psychological Review, and such a grandiose title, a probabilistic model for information storage and organization in the brain. I love the title because, as you will see, it's a very, very simple algorithm. It's incredibly simple. But it's kind of an optimistic time. And but this algorithm is attributed to Frank Rosenblatt, but actually the mathematical versions of it were known a little before that in the mathematical optimization community. There were a couple of papers in 1954 in the Canadian Journal for Mathematics or Canadian Journal for Optimization that actually had the algorithm, except it didn't look anything like an algorithm. And I don't know if anyone read it at that time, unfortunately. One way or another, the goal of the perceptron algorithm is to find this separating hyperplane given a data set. Given a data set consisting of examples with labels, the goal is to find a separating hyperplane. And the amazing thing about this algorithm is if the data set is linearly separable, then it comes with this guarantee that it will find a separating hyperplane. It's an online algorithm. It's an online algorithm. That means that it operates on one example at a time. It's a mistake-driven algorithm. That means that it operates in this mistake-driven protocol that we just saw. An example comes in, it makes a prediction, and if the prediction is wrong, it updates the hypothesis. And only if it updates the hypothesis, only if there's a mistake. If there's no mistake, we don't care. And one of the things about an algorithm that was invented in the 1950s is that it has had a lot of time for variants to be invented. So there are many, many variants of the perceptron algorithm. We'll see some practically useful variants after we see the actual algorithm. So without much ado, let's look at the algorithm itself. The input to the perceptron algorithm, the original version of the perceptron algorithm as invented by, described by Rosenblatt, the input is a sequence of training examples. Each training example consists of a pair, an example, a feature vector x1 paired with the label y1, a feature vector x2 paired with the label y2, and so on. The labels are -1 or a 1. Each xi is a d-dimensional vector. It sits inside Rd. The algorithm starts off by initializing a weight vector. And here, I'm not showing the bias term. The actual algorithm needs to update the bias term as well, but we don't need to see the bias term because we can fold the bias into weights using a trick that I described before. So you initialize all the weights to 0. And eventually, you'll be making the perceptron algorithm will be making updates to these weights. And after all the, if the examples stop showing up, we can count learning as done and return the final weight vector. So let's see what happens between step 1 and step 3 here. It's a mistake-driven algorithm. So every time an example comes in, the first thing it does is to make a prediction. We are working with linear classifiers, so prediction is simply take a dot product of the weights and take the sign of that number. So it's a sign of W transpose X or WT transpose X at the tth weight vector. If there's no mistake, we don't care. But if there is a mistake, then there's an update. And this update here is called the perceptron update. It's a rather simple update. And I'll first just read out what's here, and then we'll interpret what this means. There's a mistake. That means WT, which is the only thing that this learning algorithm has in its memory, has to get updated to WT plus 1. So WT plus 1 is nothing but the weights WT plus xi, the features, times yi times some number r. R is called the learning rate. So this is the entirety of the perceptron algorithm. So WT and WT plus 1 are both d-dimensional vectors. X is another d-dimensional vector here. So if there's a mistake, what you do is you multiply the label, which is a -1 or a 1, with the feature vector, and then multiply that by some number r, which we'll talk about later, and then add it to the weights. This is the entirety of the perceptron learning rule. Now, I want you to think about this. There's no reason why this should learn. There's no reason why this should work or do anything interesting. So let's see why this works. But before that, just a few sort of a little bit of housekeeping here. The prediction I say is sine of W transpose X, but you need to always have a bias term B, but the bias term can be treated as a weight associated with a constant feature and get folded into the weight vector. So I'm never going to show the term B here, but in every single algorithm that I present for linear classifiers, always assume that there is a bias. Otherwise, this will be an impoverished model. And the other sort of a housekeeping thing is for these algorithms, it's a little bit more convenient to represent false as -1 and true as +1. And for some other algorithms, it's more convenient to represent false as 0 and true as 1. You'll figure out from context. The general rule is whenever we are doing things with vectors and such things, it's more convenient to represent false as -1. This is a common source of a bug that I have noticed. The data set might have labels +0 and 1, and you implement this algorithm and it doesn't work. So if the data set has labels 0 and 1, just convert it to -1 and 1. Okay, now let's look at the update rule. The most interesting part of the algorithm is inside the box there. The label y can either be +1 or -1. So +1 means the true label is yi here is a positive. So it's a positive example. And when there's a mistake on a positive example, this update rule becomes wt + 1 is wt plus r times x. When there's a mistake on a negative example, it becomes wt is wt minus r times x. So let's reflect on this a little. If an example is positive and the perceptron makes a mistake on it, then the rule says add the example to the weights. There's an r there. Let's pretend r is 1. So if there's a mistake on a positive example, you just add the example to the weights. If there's a mistake on a negative example, you take away that example from the weights. That's the entirety of the update rule. Why should this work? R here is a learning rate. It's called a learning rate. Sometimes it's called a step size. It dictates how quickly the algorithm converges on the concept. If it's too large, the algorithm can kind of you need a sweet spot. If it's too big, the algorithm might jump around quite aggressively. If it's too small, then it might take forever to get to the answer. You need a sweet spot, and the way you find it is using cross-validation. This is the hyperparameter for the perceptron algorithm. Note that there's only the only time the weights get updated is if there's an error, if y prime, which is the prediction, is not equal to y, which is the ground truth. So it's a mistake-driven algorithm. The other thing to note here is, in most cases, you don't actually write this as two separate steps. You combine the step 1 and step 2 into one thing, because by noting that, I'll pull up a slide here. If yi is, let's consider all cases. If yi and y prime, yi is the true label and y prime is the prediction. So if yi is +1 and this is +1, there's no mistake. +1 and -1 means there's a mistake. If yi is -1, the predictions are +1, there's a mistake. Both are -1, there's no mistake. But why is the prediction plus or minus? That's because W transpose X, if it is +1, it's +1 because this is greater than or equal to 0. The reason y prime was -1 was because W transpose X was less than 0. Similarly, this is right. So if yi is, sorry, if y prime is, the reason y prime is plus is because W transpose X was positive. The reason y prime was minus is because W transpose X was negative, but the update happens only in these two rows. So the update happens when yi is +1 and W transpose X is less than 0, or if yi is -1 and W transpose X is greater than or equal to 0. Notice that I can combine, I can make all of this, write all of this very simply by considering yi times W transpose X. If you multiply yi and W transpose X, in the first case, it's negative. You're multiplying +1 with a negative number, so it's negative. In the second case, you're multiplying -1 with a positive number. In both cases, YW transpose X is negative. That means you make an update only when YW transpose X is negative. That means I can write these two rows as saying if YW transpose X is less than or equal to 0, then make the update. You don't have to actually make a prediction and then check. You can just say if YW transpose X is less than or equal to 0, you make an update. It's a tiny technical detail, but it turns out that this technical detail becomes useful eventually when we start talking about loss functions and such things. But any questions about the mechanics of the algorithm? Let's not worry about why this works. Do you understand what is happening here? Any questions about if you have to implement it, could you do it? Ask me a question. Either you all get it or you're all too shy. I can't tell the difference, so I will charge on ahead, and if you have questions, interrupt me.
I guess I have a question.
Okay.
So we're gonna update each weight, right? So we'll have like, let's say we have D features, that means we'll have D weights.
Yes.
Right? And we're gonna update each weight.
Yes, that's right.
Okay.
This is the vector sum.
I see.
The plus there is a vector sum.
Right.
The convention I'm using here that may not be very visible is vectors are bolded and real numbers are not bold. So W and X are vectors, so you're adding two vectors, so every weight gets updated.
Right, okay.
And R and Y are real numbers, so it's really multiplying R and Y to that vector and then adding to the W.
Right.
Which means, by the way, if you're implementing this, you should start thinking about using vector libraries. If you're implementing this in Python, I would highly recommend using something like NumPy, because NumPy does these things very efficiently. In fact, for your homework, we would recommend using NumPy. This is the simplest version of the algorithm. We'll see other more robust versions very soon. Yes.
Why is it that the final weight vector is being returned here and not, for example, the first weight vector?
Well, the first weight vector is literally the 0 vector.
So when we have this WT plus 1
Mhm.
and WT, is that saying, let's take, for example, we're dealing with the first weight, or the second weight, W1.
Mhm.
When we perform the update step, we're updating weight 2 with the value of weight 1 being updated, or?
No, we are tossing out, we are basically adding R times X or R times or subtracting R times X to W1 to produce W2.
Okay.
So I don't understand your question, maybe.
I'm seeing how the update step is working now. I was thinking that we would have a set of weights at the end, like we would have the first.
Oh, no,
weight, the
we'll
second.
return W if the for loop goes on for 10 steps, then you'll return W10.
Okay.
Or no, if the for loop goes on and there are 10 mistakes, because T is incremented only when there's a mistake,
Right.
you'll return W10.
Okay.
Yes.
Isn't there like a possibility of like the future, updated weight kind of brings the previous one?
So that's a good question. The question was, I have changed the weights here. Isn't it possible that by doing this, maybe I have ruined the label for something that some example that came before? It's entirely possible. And the amazing thing here is we'll see this perceptron mistake bound theorem that shows even if that happens, it won't happen more than a finite number of times. It can only make a finite number of mistakes, provided the true concept is linearly separable. Yes.
So is that kind of the purpose of our learning rate to try to avoid doing that?
Sort of. There are variants of the perceptron algorithm that try to find a learning rate so that at least the most recent example doesn't get clobbered. There are variants of that, but in general, it doesn't really, you can't avoid it. Let's look at every time you see a learning algorithm or any algorithm, I would say, there are different levels of understanding that you need to work with that. First, you need to understand what it is, the mechanics of the algorithm. Here, the mechanics of the algorithm is if YW transpose X is less than or equal to 0, you update the weights using this rule. That's literally the entire algorithm. The next thing is try to get an intuition for why is this interesting? Why did someone actually write this down, give it a name, and make a big fuss about it? Would you have written this down and had a New York Times press release about it? Which, by the way, did happen. So why is this interesting? And to see that, you need to look at the intuition behind this updating. So let's now consider a simple case. Let's say that the learning rate is always 1. And let's say that you have made a mistake on a positive example. Let's see what happens. What's going on with the weights? If there's a mistake on a positive example, that means the true label Y is positive, and the current set of weights has made a mistake. That means currently W transpose X is negative. That's the only reason this thing will trigger an update, right? So what happens now? There's an update. So we're going to create a new weight vector. Let's say R is 1. So it's a mistake on a positive example. So it is WT plus the example that we just saw, X. So WT plus 1 is WT plus X. Now, the cool thing to do is, the interesting thing to do is to ask for these new weights, what might the dot product with the current example be? So I can ask, what's the dot product of WT plus 1 with X? So rather than just showing you, I'm going to write it. I can ask, what is the dot product of WT plus 1 transpose X? But WT plus 1 is simply WT plus X transpose X, which is WT transpose X plus X transpose X, right? Now, what do we know? We know that WT transpose X was negative. So this part was negative. We can ask, will this thing still be negative? Maybe it will, but look at X transpose X. X transpose X is like X squared. It's a positive number. So you started off with something that was negative, and you're adding something that's positive. So this, after the update, WT plus 1 transpose X is less negative. It may even be positive. So you're making it, you've made progress. Does that make sense? Your original weight vector was creating a score. I call this thing WT transpose X. I call that a score. Your original weight vector was creating a score that was negative, which was not good because for this example, you needed a positive score. And one way of making it less negative is to add a positive quantity to it. And literally just saying WT plus 1 is WT plus X makes the new weight vector score less negative, or maybe even positive because we are adding this quantity here. If you don't like what I have typed, if you don't like my handwriting, There's a typeset version of this that's exactly there. Turns out, for a positive example, the perceptron update will increase the score of the assigned to that input. The score for that input was originally negative, and now it's going to be less negative, which is better. Turns out you can make the same argument also for negative examples. I will leave that as an exercise for you. If you don't like algebra, let's look at the same thing through pictures. There's a nice, because linear classifiers have a nice geometry, the update rule, the perceptron update rule is so simple that it has a neat geometric interpretation as well. Here I'm showing weight vectors that go through the origin. You don't need to, but it just makes the pictures easier to draw. So you have a weight vector. I'm calling that W old. And the first thing is a new example comes in. Let's call that X, and it's a positive example. So X, comma, plus 1. And you can think of the dot product of W and X and all that stuff, but the pictorial version of this is the weight vector is pointing in that direction. This hyperplane says everything on that direction is positive. Everything in this direction is positive. X lies on the opposite side, so X gets predicted a negative label. So there's a mistake on a positive example. So we can ask, what does the perceptron update look like on this plane? The perceptron update is simply, for a positive example, is W new is W old plus X. Learning rate, let's pretend, is 1. Plus yx, where y is equal to plus 1. So X is this vector here, right? You remember your vector addition rules, right? How do you add two vectors? You put the head of one vector next to the tail of something. I don't know, there's some story around that. Some parallelogram shows up, and you complete the thing, and you get a new vector here. So the sum is this, the resulting weight vector is this new vector here. You originally started with W old being this way, and then it has gotten essentially rotated this way. So what's happened is, not only is the weight vector rotating, but the hyperplane that is defined by the weight vector has rotated. The update has essentially turned the hyperplane so that, in this case, I have taken an extreme update so that the example gets correctly predicted. It's now on the positive side of this hyperplane. So we are done for this example. You can do we can have the same argument for negative examples also. So let's say your weight vector, W, originally points in this direction. And you see a negative example that's situated here. The label is -1. And there's a mistake on a negative example because it's the weight vector, the hyperplane assigns all of this region to be positive. So we need to make an update. The update is W, again, it's the same update. W is W minus Y times X. Learning rate is 1. Y is -1. So that means we need to now, to this weight vector, we need to add this vector here. It's the opposite, Y times X, so it's -X. So if X points in this direction, the opposite of that is here. So we are adding -X to W, and that takes your weight vector to this new place. So you have a new weight vector. More importantly, you have a new hyperplane that has been rotated. And it just so happens this update in this cartoon example, the update is so extreme that after the update, the new weight vector places the example on the correct side. Any questions about this? Yes. So I think the question you're trying to ask is, what if the pluses and the minuses are not cleanly separated? Then we have no hope. The perceptron algorithm, the guarantee that you'll see, only applies if the data is linearly separable. If the data is not linearly separable, we have no hope. A few years ago, a student who used to work with me got very excited about this algorithm and wanted to make an animation. So I'm going to see if I can play that. Oh, I can't play it because I don't know how to play it anymore. Oh, yes. So you have red points and blue points, and the goal is to separate them. You start off with some random weight vector. It turns out you don't need to start with 0. You can also start with a random weight vector. And in this situation, what we have here is the accuracy is 72%. The accuracy shows up on top. In the first iteration, you're not doing much. You're picking an example. And specifically what's happening here is there is a certain example. This point here, the circle that becomes bigger, is the current example that's being considered. So that particular circle, which is roughly around 0, 0, is on the blue side, but it's a red example. There's a mistake, and it triggers an update if the video. Oh no. Okay, so much for that. I'll post the video on Piazza. It's playing here, but not there. Okay, so we can't do this anymore. It's a nice video. I'll post it on Piazza. You can take a look at it. Basically, it picks an example, a random example, and then you'll see that the hyperplane keeps rotating around. And then eventually it'll kind of settle into something that's reasonably good. It's a shame. That's a nice video. It doesn't play. Okay, we have 4 minutes left. In those 4 minutes, I'm going to introduce at least one variant of the perceptron algorithm. So there are many variants of the perceptron. What we just saw was the version that was originally introduced by Rosenblatt. Oh, you know what? I'm not going to introduce the variants of the algorithm. Instead, I'm going to give you a little bit of a history here, because there's a nice historical analogy to current news. The perceptron algorithm was invented in 1957 or 58, and it became huge. It was, I'm not kidding. This is such a simple algorithm, right? If you make a mistake, if it's a mistake on a positive example, you add the weights. If it's a mistake on a negative example, you subtract the weights. That's literally the entire algorithm. But it was featured in the New York Times and the New Yorker and all the big newspapers of that time. And the hyperbole was unbelievable. It's almost like the kind of stuff that we see in the New York Times today. So I'll zoom in here in case you can't see it, because the Navy revealed an embryo of an electronic computer that it expects will be able to walk, talk, see, write, and reproduce itself and be conscious of its existence. Just to kind of remind you, it's W equals W plus Y times X. It cost $2 million. It's a class homework today. And it was, the hype was amazing. It led to many other work, and it led to popular press like this. And the cool thing, or the interesting thing, was this was built on, this was created on, implemented in the IBM 704, which is actually that box there. This is the computer. And it looks nothing like the computers that we have today. This was, I think, made with vacuum tubes. And you had to be in a very privileged position to be able to actually do anything with that. There were maybe 4 or 5 of these in the world. And I think it was not even implemented there. I just saw this one thing. It says the first perceptron is yet to be built. Anyway, the hype was incredible, but it also led to increased expectations. The 1950s, the 60s, there were many people trying to say the perceptron can do this, can do that. And then eventually in 1969, there was a book written by Marvin Minsky and Seymour Papert called Perceptrons, which was actually one of the more, not more, but one of the early attempts to analyze these things from a mathematical, geometric point of view. among other things, that book also pointed out, the perceptron cannot actually learn the XOR function. Why? Because the XOR function is not linearly separable. The perceptron can only learn linearly separable things, and it cannot learn the XOR. And that led to, among other things, that led to a huge crash in the hype, and is credited for one of the reasons for leading to the first AI winter. On that somewhat pessimistic note, I'll stop, but in the next lecture, we'll look at variants of the perceptron algorithm, and we look at the perceptron mistake-bound theorem, which is an incredibly beautiful piece of math that shows this algorithm will stop making mistakes after making only a finite number of them. Okay, let's stop, and I'll see you next week.